Hi, and welcome to the problem session for Lecture 4. In this lecture, we're going to discuss taking derivatives using the rules from the chapter. And we're going to begin with an example that uses all 6 rules that we covered. Okay, so there you go. Now, here's an example of a function that's another function inside of it. We have an exponential on the outside and a complicated function on the inside. So this should signal to you that we're going to begin with some kind of function composition. So we're going to assume this is equal to h of g of x, with h of x from the outer function, e to the x, and g of x from the inner function, x plus 1 natural log of x minus 1. Now we're going to need h prime and g prime for this because the chain rule, which is the rule you apply to composite functions, says that f prime is going to be h prime of g of x times g prime of x. So we need both h prime and g prime. Well, h prime isn't so bad. We can use the rule that the derivative of the exponential is the exponential back again to get us here. So now we have h prime, and all we're going to do to get h prime of g of x is plug in for x here, for g of x up here. We'll do that later. To get g prime, we have to use a few rules. Now g prime is going to equal the derivative of, and I'll write this out in detail, natural log of x minus 1 prime. Now, first rule we're going to use is that the derivative is a linear operator. So we can split up this derivative into two pieces. Because recall, if g equals a plus b, then g prime equals a prime plus b prime. So this thing is going to equal a derivative of that minus derivative of 1. Derivative of 1 since 1 is a constant, its derivative is 0. So we're using the power rule that says the derivative of any x to the 0. In this case, 1 is just x to the 0. The derivative of this is just 0 because the power rule says the derivative of x to the n equals n x to the n minus 1. So this is going to be 0. Get rid of that. Now we're over here. Now we have a product of two functions, x plus 1 and the natural log of x. So we use the product rule, which says that if you have uv, then g prime equals the derivative of the first times the second, plus the first times the derivative of the second. So now this becomes x plus 1 prime natural log of x plus x plus 1 natural log of x prime. Now, the second one uses the rule for taking derivatives of the logarithm. The derivative of the logarithm is just 1 over x. So if g equals log of x, then g prime equals 1 over x. That's the rule for that. So that's 1 over x. What about this? What about the derivative of x plus 1? Well, now technically speaking, we're going to again use the rule that the derivative is a linear operator. So you have x plus 1. The 1 differentiates to 0. So all we care about is the x. The derivative of x is 1 because using the power rule, you pull down the 1 and subtract 1 from the power. You get 1 times x to the 0. X to the 0 is 1, so it's just 1. So putting it all together, you get 1 natural log of x plus x plus 1 over x. And we're done. Put them all together, we get f prime equals h prime, let's see the x, of g of x. So when you have h prime of g of x, you plug g of x where the x is in h prime. So now you plug back in up here. And you will find in general that when you take derivatives of exponentials, you get back the original exponential again, times the thing in the exponential, rather times the derivative of the thing in the exponential, which is g prime, which we just said is natural log of x plus x plus 1 over x. There you go. We did a fairly complicated derivative, and we used all the rules from the lecture. Okay. So I'll do one more example that's also a little bit complicated. Again, I'll often do more complicated examples in the problem sessions, not always, but often, because it gives you a better sense of what you can do, and then you can do a bigger variety of problems in the actual problem sets. and the book as well. Okay, so here's another example. F of x equals e to the 5x squared. And again, as I mentioned in the various points in the lectures and the introduction, I believe, I will try to keep things on one screen because it's easier to pause and read it. Occasionally that means I write kind of small. I apologize for that. But I do think it's important to have it on one screen so you don't have to keep fast forwarding back and forth to understand stuff. You can just pause it and read it on the screen at once. Okay. So again, we have multiple functions, and again, we're probably going to use more than one rule. First, we know we have a quotient. You can use the product rule, we can use the quotient rule. So what I'm going to do is use the quotient rule effectively, the same as the product rule, just easier to. We focused a lot on the product rule in the book because the product rule is the fundamental one. The quotient rule is easily derived from the product rule and the chain rule. But here it's good to have an example which actually just use the quotient rule. They're the same thing. So we're going to set g of x equal to the numerator. And note this thing is still more complicated, so we might have to deal with it more later. And h of x equal to the denominator. So g is the numerator, h is the denominator. Now the quotient rule says that you have g prime times h minus g of h prime divided by h squared. And again, we show in the book how they're just derived from the product rule and the chain rule together. So there you go. Here are these two things. Now we need g prime and h prime. Let's start with, now both, however, require us to use the chain rule. So let's do g prime first. Let's set up some functions here. Now g prime here is going to equal, g prime here is the exact same logic as the previous example we gave. So again, it's going to be the exponent back again times the derivative of the exponent. So it's exactly the same as previously. Here it's a little easier for us. All it is a polynomial in x. So we can use the fact that the derivative is linear to deal with each term in the polynomial separately. And use the power rule to get down all the, to compute all the individual derivatives of all the individual terms. So the first one, so the first one in red here is the derivative of 5x squared. You pull the 2 down, 5 is a constant, so it just stays there. Derivative is linear. So you pull down the 2 from the x squared. 2 times 5 is 10. So you have a 10 out front here. Then you subtract 1 from the exponent to give you x, because 2 minus 1 is 1. Now the next term over here, blue, keep the minus 1 out front. The derivative of x is just 1, so it's minus 1. And then finally the green at the end is a constant, so its derivative is 0, so we're going to ignore it completely. And we'll close it off like that. So there's g prime. Now how do you do h prime? Again, it's similar, but a little different. Again, the chain rule, because we didn't just do this example, we'll actually go through and do it in more detail. How do you do this? Well, again, you're going to, well, here, let me add a step. So now h is going to equal, we'll call them, let's see, we'll call them r of s of, excuse me, s of x, where r is the natural log of x minus 1, and s of x equals x cubed. So again, we have the chain rule, which says that h prime is going to equal r prime of s of x times s prime of x. Now, s prime of x, just the same, is x. S is x cubed. S of x, so x prime of that is, using the power rule, 3x squared. You just pull the 3 down and subtract 1 from the exponent to get that. What's r prime? Well, r is the natural log of x minus 1. The derivative is linear, so you can treat each term separately. The derivative of negative 1 is 0. The derivative of natural log of x is 1 over x. So we have r prime is just 1 over x. So r prime of s of x is 1 over s of x. So that's 1 over x cubed. and then you multiply that by s prime to get the whole thing, which is 3x squared divided by x cubed. Oh, I forgot the minus 1 over here. I apologize. That's right. That's right in the first place. Sorry. Which equals 3 over x. And that is h prime. So now I can finally put them all together and get e to the 5 x squared minus x plus 3 times 10x minus 1 times h, which is natural log of x cubed minus 1, and divided by, minus. It's a very long one. I should have left more room. Let's do this. Minus, what's next? G, which we write this again. Should have taken that in both terms, make my life easier. And times h prime, which is 3 over x, and divide the whole thing by h squared, which is natural log of x cubed minus 1, 2 squared. And that's it. That's the whole thing. So we've done another really complicated example, but just using the rules. And the key point here is we can use the rules to break down the function into smaller and smaller pieces until we have individual pieces that we can apply our basic rules, either the power rule or the derivative exponential rule or the logarithm rule, to get our answers, and then build the whole thing back up again to finish it off. Okay, and that is it. The next lecture we're going to move on to integrals. Thank you very much.